Good morning. It is November 7th, 2015, and today we are doing match. So this Saturday, November 17th, 2015. My name is John Rader, and I am currently waiting for my partner teachers from the outer island to populate the chat room. For now, I'll put it on mute and wait for them. Good morning, Lokalani. You don't want to use your microphone? I ask you, is the audio feed better today, or is it worse or same? Your audio feed's okay. You're not a morning person, are you? Yeah, I figured. Okay, we're just waiting for everybody else to show up. So the few other people that are supposed to be here were so waiting on Marcia and Sue. I think Jessica that was here last time, she was just on. She was just traveling, so I don't think that she's going to be here this time. If anything, she probably is going to show up directly. So, but yeah, we're just waiting for them, so we can just cruise for a little bit. So, do you have any questions before we begin? By the way. Okay. Okay. I'm going to go on silent until some other people show up. So we'll give them about, I don't want to say 30 minutes, but probably around 8:50. If they're not here, we're definitely going to have to start. Okay.
Okay. Can
Yeah.
you hear me though?
Yeah, it looks good. Sounds good.
Okay. Okay. Thank you.
Yeah, no worries. Thank you.
Hey.
How are you doing? Long time no
Good.
see.
Yeah.
Did we lose one on Molokai? I can't hear you,
I'm
Lokalani.
still here.
Oh, okay. Just making sure. So, we're just waiting for oh, nice. We're just waiting for the room to populate. So we're expecting at least one other from the Big Island.
Cool.
That would be Marsha. And so now we're just cruising. So we'll start around 8:50, 9 o'clock, depending on who gets here. So I'm just going to put it on mute for now.
What's up, Sue?
I just was in the water. The waves are nice. It picked up. Oh, you still can't hear me. Yeah? Why does it always do?
No, we can hear you. You're
Oh,
fine.
good. Hey,
Yeah.
I always get confused with that mute microphone symbol because, it's got the cross through it and it looks like
Mm,
my microphone is muted, but I guess it's not.
yeah. Only you can mute your own microphone, or I can if I want to, but I don't ever do that. I leave it to
Well,
you
you
guys to
can
do.
do it if you want to. You can cut me off.
No, 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 no. I don't want to do that. Where'd you go surf today?
Oh, my connection is slow. How do I make my connection faster?
I don't know. Yeah. I think that's just a function of being over there. I think that's just the nature of the beast. So, one thing you could do is if you're having real problems with streaming, is that you can turn off your video feed by mousing over the screen and just turning off your webcam.
Okay.
Yeah, but it seems like it's all right now. I just don't want you to miss anything. So if you feel like you missed something, just let me know.
Okay. Sounds good.
Okay, I'm gonna mute up.
Gotcha. Okay, so where was I? I am looking at this stuff. Yeah. Over here. Alrighty.
Susan.
Wow, that is slow.
Hello?
All right.
I'm here with Kelly. Hi!
Hi, Kelly.
Sorry,
Um,
we had some connectivity issues. This is our first time setting up at her place.
nah, no problem. No problem. Just wanted to make sure you guys made it. Um,
Yeah, this is John.
so, yes, I am John. Uh, I'm glad to see you guys this morning. We're going to start here in about 5 minutes. So we'll start with the pre-session write-up, and then we'll go from there. So for now, if you guys just want to mute your mic, we're just waiting for one more person to see if she even shows up. Okay?
Okay, and was there an email? Because I didn't recall getting an email like there was last time to fill out anything.
I don't think so. I didn't send any emails, so I'm not sure what you meant by fill out anything.
Oh, for like the pre-write-up? I thought that was like
I
I
sent.
gotta.
I'll send that. I'll send that.
Oh,
Yeah. So once we get started, I'll send all that out.
okay, perfect.
All right.
Thanks,
Yep. Talk
John.
to you in a minute.
Okay. Hey, John, this is Jessica. I have another quick question for you.
Yeah. Go ahead.
Um, do you want Kelly and I, since we're both working together, this is my computer, when we do the write-up, should we do it as a team on, for just one for the both of us, or does she need to,
Do it separately.
yeah,
Yeah, I think she needs to do it separately. A lot of that depends on if you're doing the PDE 3 credit or not.
we
So
both are.
okay, if you're both doing the PDE 3 credit, then you both need to do it separately.
We both need to, okay, so,
Yeah.
so we'll do the Google Hangout, like this session live together, but then you'll send her a separate link to fill out the pre-session?
I send the link in the video window, and you can just give it to her.
Okay.
Yeah. Does she have a computer?
Yeah, we just weren't sure if she needed to set it up and get ready or not.
Uh, no, I don't think so. I mean, if you want, I can add her into the chat, and if she has a webcam, great. She can turn it on. If not, she didn't have to. But that way, she would have all the links there, and she could just watch what's happening if she wants. If not, she can just take the link from the window. They're all shortened Google links anyway.
We'll just do that. We'll just share and then she'll get the link. That sounds good.
Okay, that's fine.
All right, thanks, hon.
Yeah, no worries. Okay, good morning, everybody. It's about that time to start. I don't think we can wait all day for everybody to show up, otherwise we'd never get anything done. So at this time, I'm going to go ahead and post the link in the window for the pre-session write-up. So if you would, go ahead and click on that, and then I'll give you the topic. And I'll also post that in the window as well. So the topic for today is about numbers. Okay, can everybody see that link?
No, I'm working on it.
Okay. Can you see the chat window, Jessica?
Oh, wait, there. Okay, I got it.
Yeah,
Good.
okay. Okay. And then Loki. Missed that, thank you. And then is Sue around? Yeah, exactly.
Yeah, I'm here.
Okay. All right. Just wanted to make sure everybody could do that. So I give you guys till about 9 o'clock to work that out, 9:05, somewhere in there. And then we'll go from there whenever you get done. Two small announcements that Linda and Sean asked me to make, which were if you're doing the PDE3 credit, that the pre-session and post-session write-ups, you should hold on to those. They're going to start sending them after each session is over. So you should get a copy of those today. If you don't, you need to contact them. And then also, if you are doing the PDE3 credits, that they encourage you not to wait to the last minute to start putting your information together. So the sooner the better. The reason for that is that what usually happens when people do that is they completely forget what a whole session was about, what their thoughts were about on the sessions. So they just want to make sure that people don't forget when they get to, March or April or May, and then try to remember what happened in September, October, and November. So be proactive in your approach to your PDE3 credit. Yeah. Okay. If you have any questions, you can always ask me, and I'll direct them at them. Jessica, if you can you type the name of your compatriot there in the window just so I have that for my records? Does anybody need any more time? Okay, I'll assume by that lack of response from everyone that no one else needs any more time. So at this point, I want to go ahead and start the math activity for today. All you need for the activity would be a pen or pencil, piece of paper, and a ruler if you even need a ruler. You don't even really need a ruler for this one. Okay. So what we'd like to do is start out by, on your piece of paper, drawing yourselves a line. Okay, so very simple. Let me see if I can find an eraser here. Perfect. So what we're going to go about doing is drawing ourselves a line. And then whenever you draw yourselves a line, we need to go ahead and pick on the line a starting point. So what would you like your starting point to be on your line?
5.
You want to be 5? Okay. So how do I denote the number 5 on this line? Where is the number 5?
Right in the middle.
Okay, so you want to define it to be right in the middle, and that's fine. So again, no, that's fine. I mean, you know, whenever you're dealing with students, they might say 17. You never know. So if we're going to designate where 5 is, though, how do you know that 5 is in the middle, right? So you just said put 5 in the middle. Where do most graphs start from?
0.
Right. So what we would define is say, let's start from 0. So if 0 is right there, where is 5 then?
To the right of 0.
Okay, so we've made some designation about the number line. So we've defined to be positives are over to the right and negatives to the left. By the way, can I confirm, on my image it's flipped. Is it flipped for you guys also?
No.
No, it's
Okay. Okay, just making sure because it looks flipped on mine, so I have to think in reverse when I look at the screen. Okay, so if positives are to the right and negatives are to the left, we said, okay, 5 is somewhere on the right side of 0. So how far do I go? So I'll start at 0. You just tell me when to stop.
Stop. Nah.
Stop right.
I
No?
don't know. It depends on what your
scale is.
There you
Okay.
go.
So that's the word we're looking for. So anytime you're trying to navigate on a map, you need, if you look, they have the legend on a map. What's in the legend? It tells you where you are, it tells you where to start from, and it tells you a scale point. So it gives you directions and scale. So we have origin and direction. Direction's only left or right in this case. So we need a scale. So why don't you tell me what's my scale here? I'll go out a distance. How far do you want me to go?
Keep
How
going.
about right here? Keep going?
Go by. No. Yeah, right there.
Okay. What would you like me to call that?
Pretty.
Pretty? Is that what you said? Okay, what
Sorry.
coordinate,
Okay.
where am I in space then? How about that?
Again, depending on your scale. So you,
Okay.
let's call that 2.5.
2.5. Okay. So again, it's your choice whenever you're setting your scale. You can always set the scale to be whatever you want. So I could have very easily called this distance 3. I could have called it 1. I could have called it 0.2. It doesn't matter to me. Okay.
We could have called it 1,000.
We could have called it 1,000. Again, that's important. I think students, whenever they see the line, if you make just, you know, any mark somewhere, they're tempted to say, oh, that's 1. That's the number 1. But it doesn't have to be. You can choose it to be any number you want. Okay. So I'm going to scoot back a little bit. If you're going to call that 2.5, I'm actually going to go in and mark my standard 1s on there. Okay. Mm-hmm. Then after that, it should be easy to find 5. So where is 5 from there? I would go over, and I could do it 2 ways, right? How could I get to 5 from 1?
Make 4 more marks.
Okay, so I could continue.
Distance, like that first one.
Okay, sorry, I'm reading a message to, I think the convention placing 0 in the middle does not appear until grade 6. Yeah, that's true, so that's a good point. Why do we put 0 in the middle anyway?
Easy.
Convention, easiness. Some people told me that 0 is the middle number. Is 0 the middle number?
No.
Well, we don't know, right? The numbers go out to positive infinity and negative infinity. We can't say for sure what middle even means when we're talking about the numbers. Yeah, right, not until the negatives are introduced, as Sue says. So the whole idea is, why do we start from 0 anyway? The best argument for that I could think of is that 0 is both, it's neither positive or negative. Or if you prefer, it's both, right? It could be both positive and negative. Another argument is that 0 is the average of all the numbers on both sides of the line. So why not start at the average of everything?
I like that.
Yeah. Yeah, I've heard a lot of arguments. And again, I think most people like 0 too.
Zero, the only number that doesn't have an opposite, right? It's. You know what I mean?
It's its own opposite.
Oh.
Yeah. So, I mean, again, when you say the word opposite, you're meaning changing the sign in front of it.
Yeah.
Yeah, yeah. So if you put a negative in front of 0, it's still 0. So it's its own opposite.
I like the idea that it's our start value.
Yeah, I think most people, once you get the idea of what, playing with 0, why 0 is so nice. 0 is actually my favorite number. I know everybody says that pi is theirs, but 0 is actually mine. Okay, so if we're at 1 and we want to move to 5, there's 2 ways we could do it. The first argument I heard was just go over 4 more tick marks. So 1, 2, 3, 4, and then you must be at the unit 5. Okay. Another argument we can make here, again, that was just by adding on the value 4. How else could we go from 1 to 5? What else could we do to 1 to get to 5? That's an open question. So how else can we get there?
The minor grid lines not marked off and just have like 3 and then 5.
Okay, so we would still have to add on some value here, though, right? We would still have to add a value to 1.
So
Okay.
could we go beyond 5 and then come?
No, we want to go exactly to 5 from 1.
Well,
So-
you kind of make the intervals.
Minor grid line and then do 10, and it's halfway between the two.
Okay, so that's using, again, the idea of just splitting these in half, and that's just making your scale different, right? So you're starting from a different scale and moving up to it by doing it twice as much. So instead of adding on, this would be now a half, and if you're starting at a half, you would have to go now further, right? So how would you go from a half then to 5?
Same thing. You would make the marks.
And then
Okay.
mark.
So what you're doing is, if you're going from a half to 5, how much do you have to go?
Oh, you have to do 9 copies of a half to get
Right,
the point.
which 9 copies of half would then be 4.5. But again, here, what you did is something very similar. Down here, we added 4 to go from 1 to 5. You cut it in half, you made your scale different, but we still have to add something to get to 5. We're adding 4.5. All I'm asking is, instead of adding, is there another way to go from 1 to 5? All right, and Jessica says 1 minus negative 4. Okay, again, we're subtracting a negative number. Subtracting a negative number is still 5. Oh, adding. Oh, hang on, everybody. Hi, Marcia. As she immediately mutes. Apparently the dog's making a lot of noise. So we had just started, so welcome in Marcia Chose from Big Island. Marcia, if you look in the chat window, I'm going to post the link for the pre-write. Okay, and then you need to go about doing that. We just started the math activity, so you've got a little bit of time. You can work on that actually after if you want to. So let me just post that link real quick. Hang on. So there's the link, and the topic for today, I'll also post that just so you can see it. Okay. So instead of adding or subtracting here, let's try a different operation. How can we go from 1 to 5 using a different operation?
Division.
Okay, so what divided by what on this map? If so, again, I'm going to erase the ones we did before because those were addition. How can we go from 1 to 5 using division? What do I have to divide 1 by to get to 5?
Oh.
You said division, so I'm just going with division here.
Yeah. Point something.
Okay. Okay. So
um,
how do you find that number?
I don't know. 5. I don't know.
So I'll write it out if you want as a formula, just so we can see it. You would say 1 divided by some number is 5. So what you're trying to solve is this proportion equation right here.
Oh, okay.
So you would say, okay, multiply by x, 1 is 5x, so x is 1/5. So if you take 1 and divide it by 1/5, you could get to 5 also, right? So if you're using division. But most students don't like the idea of division. Division is hard.
Yeah, it is.
So instead, let's do the other operation, multiplication. How would you get from 1 to 5 with multiplication?
Times 5.
You would multiply it by 5. So what we could do is multiply the value 1 to get to 5. Now, in reality, if you're doing addition, and I know, Jessica, you said subtraction also, addition and subtraction are actually the exact same operation. And I know we teach them differently, but they undo each other. They're inverse operations of each other.
Mm-hmm.
Addition is subtraction. Subtraction is addition. And if you're unconvinced, remember that when we say 3 minus 5, for example, that 3 minus 5 is the same thing as 3 plus negative 5. It's the same thing as adding a negative number. So they're actually the same operation, in the same way that division and multiplication are actually the same operation as well, because they undo each other. They're inverses of each other. And again, to give an example of that as well, suppose that you had 3 divided by 5. If you wanted to write that as a multiplication, that would be, what would that be? What is 3 divided by 5 as a multiplication? That's 3 times what?
Okay.
What is that? Sorry, I didn't hear you.
3 times 1/5.
1/5, right. So in reality, there's actually only 2 operations out of the 4 primary operations that we teach. It's addition and multiplication. In reality, if you want to get down to it, actually all 4 of the original operations can be written as addition only, right?
Yep.
So addition and subtraction are the same. Multiplication is just multiple additions.
Yeah.
And then what is division?
Multiple subtractions.
Multiple subtractions. So it's multiple additions by the opposite. So all your primary operations that we actually teach are all built on the back of addition, which is why addition is really important. So that's why we leave it up to the first and second grade teachers to teach addition and subtraction very soundly. They need to understand how to do that. Okay, so the idea is then we want to expand this idea. We want to have a number line and work in front of us. And what we want to do is start doing our activity. So I'm going to ask you guys to pick a few numbers on your number line. So make your number line from negative 10 to 10. Okay. You may want to actually make the scale 10 at first. So you'll want to expand it out to at most by 50 by 50. So negative 50 to 50 if you're going that large. Okay. And then what I'm going to have you do is take your number that you choose, and I'm going to have you perform some operations on it. Okay. I'm going to post those in the window and have you start. Now, the fun thing is, I know we're sitting here doing this on the computer, and that's a little bit lame when you're trying to take this into the classroom. It's more fun. What you can do with this is actually have your students, you can actually have them go and stand on a number line that you guys create. So right now the teachers are outside. They made their number line with a piece of rope, and they designated their 0 and their 1. And what we're having them do is stand on the number line where their number is originally, and then we're having them perform these operations on the number line. So if you want to take this in the classroom with your kids, it can be fun. Jessica, we'll start with 1 number at least, but if you want to do multiple numbers, you can do that. One thing that I was going to say that you could do that's really interesting with this is that you can pick a color for your original number. So say I pick 3 as red, and negative 1 is blue, and 4 is green. And then as we perform these operations, you can mark them off with the same colors as well and see where they go. So if you want to do 3 numbers, it's fine. If you want to do 1 number, it's fine. What I'd like for you to do is perform each of these operations, right? And again, you're making out the graphs for each of these, okay?
Ah, okay.
Okay, so you're not just doing one graph and then doing this over and over and over again. You're making a graph, marking where your number is, and then what we're going to do is do these operations and see what happens when you do these. Okay, so you're going to be making, I believe there's 10 of those there. 13. So there's 13 different graphs that we'll make. Okay. And again, I'll give you a few minutes. If you have questions, feel free to ask. I'm here. Okay, I'm going to mute up. If you have questions, just let me know.
Hi, sorry I'm late. Can you hear me?
Yeah, it's all good. I can hear you. So I posted the link for the pre-write in there.
Yeah, I
And
did that already.
okay, great. So you're right on track with us. Usually we start around 9, but got started a little bit early today because we already had 4 people here, and I wasn't sure if anybody was coming. So,
Okay.
but yeah. So I'm gonna mute your microphone just while we're
Okay, I
doing
can
this.
mute myself. Yeah.
Okay. All right. Perfect. Thank you.
This is kind of stupid.
I think you should mute Susan. John,
Yes.
in the instructions, after you take half of your number, see that part?
Yep.
It says multiply your number by 1. Is that your original number or the half of your number?
Okay, maybe the instructions weren't clear, so I'll just clarify this real quick. So when you're reading out these are individual instructions. So you're making individual graphs for each of these. So say for the first, yeah. So for the first one, if my number was, say, I'll mark 0. If my number's 1, I'll mark that as my original, and then the first instruction says add 1 to my number. So I would then mark where that number moves to, which is now 2.
Okay.
Then you're doing the same thing for the next one. So you're making another graph. You have 0 again, and 1 is my original number. Where does 1 move to? Then it's going to be, somewhere way over there at 11. All right, so we're just making individual graphs for these, not combining all of them together.
Okay, got it. Thank you.
You're welcome.
Hey, John. We're having
Yes.
a debate. Are we supposed to, when we're going on the number line, at each step start where we left off at previously, or
No,
go back to the original number?
you're going back to your original number.
Oh,
So,
Boom!
awesome.
so,
Thank you.
so yeah. So if you chose, so for example, for mine, I chose the number 1 as my
Okay.
starting point. So the first step would be to generate the graph. Oh, 1 moves to 2,
Right.
and then et cetera, et cetera, et cetera. So you should have 13 different graphs from that have your original number on it, and then your final number for
So do
each.
I get partial credit even though I did it
She
wong?
tried. She gets an A for effort.
That works really well until you get up to a certain education level, and then they find out that you don't get any credit for bad not following the instructions. So whatever. Well,
Thank you.
yeah, no worries.
I feel great about myself right now.
There you go. Perfect.
I'm a winner.
Does anyone need any more time? Okay, we'll reconvene in 4 minutes at 9:35 then. Okay. So can I get everybody back together? All right. So first question, moving on the list. I'm sure you all are fairly good at navigating on the number line. I mean, I don't think this should have been too much of a challenge for you. What does addition do to your number? So if you had to describe this, again, I know this activity is more directed at children when you're learning operations. So how would a child describe what's happening when you add?
It moves to the right of the number line, of the
Okay.
original number, the
Okay.
given number.
So whatever number you start from, addition should have just moved you to the right of that number, assuming you were adding a positive number. Okay, so we'll assume addition means for a positive number. And then in another way, how would we define subtraction or describe subtraction on the number line?
Move to the left.
Right. So if addition of a positive number moves to the right, subtraction should move to the left. And again, that's because it's adding of a negative number. So you're adding negatively. Okay, so addition, subtraction, fairly straightforward, not too bad. All right, what about multiplying by a number? What did multiplying do? So if you multiplied by a positive number, we'll start with that. What did multiplying by a positive number do?
Made your distance farther.
Okay, so if you multiply by any number, does it always make your distance further? I don't know what you mean by further, because further is in reference to something. So
Yeah. Further down the line of the original number.
okay, so if you always multiply by a positive number, does it always move you further down the line?
Yeah.
Are you sure?
No.
I'm thinking.
Okay, so yeah, so you look at the results that we did. If you look at your list of numbers, we had numbers double your number, half of your number, multiply your number by 1, multiply your number by 5, multiply your number by 2/3. Did all of these operations, and again, I'm just looking at the positive ones here, did all of these move you further down the line?
Multiply your number by 2/3. No.
Right. Okay, so multiply your number by 2/3 didn't? What else didn't?
Multiplying by a negative.
Okay, so we're just dealing with the positive ones first. We'll talk about the negative ones in a minute.
By 1.
Okay, so multiplying by 1 did not move you further down the line.
And by 0.
And by 0. Okay. There's one more here that didn't do that as well, but it's written differently, which was take half of your number. And again, taking half is the same thing as multiplying by a factor of 1/2. So when you say moving further down the line, right, that makes sense for positive numbers that are bigger than 1. But what about the ones between 0 and 1? What do they do?
They make your number move to the left of the given number.
Now, if you're saying to the left, is that like subtraction?
Yeah.
Is it exactly like subtraction?
Yeah.
So I want to get some input because I feel like only one person's answering here. Can
Yeah,
you guys...
I'm the only one in class. I am your GD. Do with it. Come on.
I mean, I love getting answers, trust me, but I want to make sure everybody's participating. So, Jessica, can you turn on your mic because you had something to say, but you just typed in the window. I just saw that. So.
We're here.
Yeah,
Hello.
Go ahead.
Kelly said she has something she wants to share.
Okay, Kelly, go for it.
No, that actually wasn't me at all. That was Jessica talking about it. I was in the bathroom.
Oh, okay.
No, it was Jessica.
Well, whoever's throwing whoever under the bus, can you please describe the thoughts? And now nobody wants to answer. This is awesome.
No,
Just like in the classroom.
What you guys have been saying
We're
about
hitting each other.
So if you multiply by a positive number, what does it do to your number?
when you what divide by a positive?
No,
Okay.
multiply.
Are you asking whether or not it's going to say positive or turn negative?
Well, that depends, right? So some people, I don't know what your starting numbers were. So I didn't even ask what your starting numbers were. The idea was it shouldn't matter what number you start from. Depending on what the operation is, it should do the same thing for everybody, theoretically. So say, for example, what does multiply by 2 do to your number?
Makes it twice as.
Mm-hmm. Right.
Twice as large. Okay. And multiplying by 5?
5 times.
Yeah.
Okay. So then what does multiplying by a half do then?
Makes it half the distance it is from 0.
Okay, so we're talking about now distance from 0 as opposed to distance from where our original number was. Okay.
Well, when I look at addition and subtraction, I just looked at it as like, absolute movement, whereas multiplication depends on the number, how big the hops are.
That's right. That's right.
Can I reply? Can you hear me?
Yeah, I heard you. Did everybody hear what she said?
No.
Could you say it one more time, please?
What my thought was, if the number is greater than positive 1, then your number is going to increase. If it's between 1 and 0, then it's going to either stay the same or decrease. I mean, that would be kind of like the rule or whatever if you're trying to have a definitive explanation or whatever, as far as in the positive numbers.
Right.
From 0 to 1, it's going to decrease, and if it's greater than 1, then it'll be increase.
Right.
Whatever. I don't know how you.
No, you're on it. No, you're saying it right. This is exactly the kind of thing I'm having to explain to some of my students right now, is that if you multiply by a number bigger than 1, it makes it by that much larger. It gives it's a scale factor, so to speak. And if you multiply with a number between 0 and 1, it's a scale factor, but it's going to make it smaller. So when you multiply by a number bigger than 1, it makes it larger. When you multiply by a number between 0 and 1, it actually makes the number smaller. So again, think of it as a scale factor. And what it actually does is exactly what you said, was it moves you either closer or further away from the number 0. Okay. All right, so that's what multiplication does by a positive number. What does multiplication by a negative number do?
Interesting.
It switches your result to the opposite sign. So if you started with a negative, it'll go to positive. You start with a positive, it'll go to negative.
Okay.
So it would do the same rule applies, except it's on the opposite side of the number line, if that makes any sense.
Right. Okay, so it's the same as multiplication. It just, what it does is it takes your number from one side of 0 and it moves it to the other side of 0. So I mean, I know this is not too much of a stretch of your imagination, your math abilities, right? I know when you guys saw this, you're like, listen, I know how to add, subtract, multiply. Like, this is not a stretch of my abilities. The idea is, though, we're trying to get you to think about what the operations do onto the numbers in a different sense, which is their geometrical sense. So geometrically, what we can say then is that if you add a positive number, you're moving it to the right. If you're subtracting a positive number, or subtracting, then it's moving it to the left. And then if you're multiplying by a positive number, it moves it away or towards 0, depending on the size of the number you're multiplying by. And then if you multiply by a negative 1 instead, or a negative factor, what it does is it takes it and flips it across from the one side of 0 to the other side of 0, depending on what the number is, right? So in geometry, those are what we call transformations. So the adding and subtracting of a number is what we call a translation. So a translation is moving it by a certain amount, either to the left or right or up or down, moving along one dimension or another. So say if you're on the number line, we're moving to the left or right. If you're on the y-axis, you're moving up or down. If you're on the z-axis in space, you're moving. And again, I know you guys don't do 3D graphing necessarily. And then if you're multiplying by a positive number, it's called scaling, which it shouldn't be a surprise. It's called scaling. So we're scaling it. We're moving either away or towards 0, depending on the scale factor. And then the last one, which is multiplying by a factor that is negative, is actually a 180-degree rotation of the axis. So if you're at 2, when you multiply by a negative 1, you're folding 2 and you're moving it all the way over to negative 2. So you're doing a 180-degree rotation. Okay? So I know we don't typically think of these as geometrical concepts, but that's what our operations of addition, subtraction, and multiplication are. All right. And division, for that matter, because division is multiplication. So now, in a similar way, we want to do the same thing again. So I've got a few more for you to try out. They're going to be a little bit more challenging this time. So what I'm going to do is post those in the window for you. Or are there questions? You guys? Okay, so sorry, I hadn't read what Sue read, so it depends on the just. Yeah, yeah, exactly. Arithmetic versus geometric. Okay, so do you guys have any questions before we start doing the next part here? So these are going to be a little bit harder. No? Okay. All right, so I'll post the next set of instructions in the window. So again, same thing again. You're choosing a number or a set of numbers that you would like to do these operations to. It's your choice, okay? And then you're making a graph that does these operations to you, okay? So you're trying to figure out what is it that these, how do you do these steps? So I'll post these right here. Thing I just did not work. Let's try this. So there should be, in this window, 9 of these. So anytime you see the word doing is the beginning of 1. Just so we're clear on the first one, it says doing this operation twice results in adding 10 to your number. So if my number is, say, the number 1, is the number 1, I would start at 1, and then I've got to do some operation twice that results in adding 10. So if I'm adding 10, I'll be at 11. What do I have to do to 1? In what addition do I have to do to 1 in order to get to 10?
Plus -1.
Say that again?
Plus, what addition do you have to do to 11 to get to 10?
No. What addition do I have to do to 1 to get to 11? So what operation do I do twice, addition, to get to?
Oh, got it.
Plus
So,
5.
so I
Plus
have to add 5 first to get to 6. Then I have to add 5 again to get to 11. So the first one is not going to be too bad, right? So do this operation twice results in adding 10. So I added 5 twice. Okay. So now you're trying to find what operation, and you're always going to try to find this operation that when you do it twice does these operations. So again, I'll let you think about them. I'll give you solid 15, 20 minutes to work these out. If you have questions, feel free to ask. I'm going to put it on mute. I'm here. Feel free to talk to each other, by the way, as well. I mean, there's nothing keeping you guys from talking to each other.
Doing talking points results in adding 1 to your number. 1 to your number. Doing this operation translation, subtracting 6 from your number. You have to multiply your number by 4. So times 2 times 2. That's an interesting. You have to multiply your number by 1. Okay, it doesn't matter. Ha! Times 1 times 1. Interesting. Doing the separation calculus and multiplying the number by 2. Huh. Here's multiplying the number by 2. That one comes stuff. Cool. Times 2. Times 2. 2 and 48. Plus 12 plus 12. Huh?
Are we having fun?
Yeah.
Eh.
At least these operations are a little bit more interesting than the last ones, I think. But again, we're talking about a starting point when you're trying to present this to children. And I think that at least understanding what visually addition, subtraction, multiplication do, I think it makes more sense.
But according to you, I don't need to teach subtraction or division. I just need to teach addition.
That's it.
Addition,
That's it. That's it. You're welcome. I think if you can get your children, your students to understand that all the operations are actually addition, and that also includes exponents, even though we didn't talk about it, because exponents are just multiple multiplication, and multiplication is just multiple addition. So that's multiple addition done multiple addition times. Of course, that's really hard to explain to a child, whereas exponents not so bad.
Let's do it. Oh, square root of 10. Weird. Huh. That's weird. Awesome. I like that one.
Interesting. By -1, -1. Okay, so negative. How can you get a -1?
And that one actually took me a minute to think through. And then I finally figured it out. I just had to think about it for a minute.
I square root of -1. Oh, I. I don't know. I don't know. I don't know. That's when I shiver Tasho. I square root of -1. What would that be? What's the square root of -1? -1 times the square root of -1 equals I. Yeah. No. Transformations.
Yeah, for all of you, by the way, I know you guys are still working on that, that's fine. So the idea is you want to have you want to try and figure out what the operations are that are performed and visually what happened to your number.
Yeah.
You also like to think about it in terms of the transformations that we talked about. So scaling, shifting or translation, and rotation. So again, just try to think about those. I don't expect you to have all the answers, but it'd be a good idea to if you could describe each of these operations as either a transformation, as what type of transformation are they? Are they scaling? Are they translating? Or are they rotation?
Hmm. Hmm. This one. Mhm. Honey back on. Yeah, I get that. Yeah.
Does anyone need more time?
Nope, I want to hear the answers.
Jessica or Marsha, do you guys need more time? You have to keep scrolling back on the chat window? Oh, I'm sorry. Um, Let me see. How far? What number are you on? 8. Okay. Okay. So we'll give you about 5 more minutes. Maybe we'll talk about 10:10. How about 10:08? 10:08, somewhere in there. We'll talk about it then.
I'll do something else. Okay, do something else. So what is this? This is that 84. Okay, so this is grade 5. Say this. Grade 5. Okay, next one. Go, go, go. This one. Good. Error. Error. 999. Grade 6. I can make it. And my call unit ready. Here. It's so weird. Huh.
Okay, you guys are ready, I hope. So just starting on that list, so if we wanted to go through on the first one, I did the first one, which is doing this operation twice results in adding 10 to your number. So that would be adding 5, then adding 5, right? So we understand how to add, that's no problem. How about doing this operation twice results in adding 1 to your number? How do we add 1 to our number? So
At half.
right, so we would have to add a half and then another half, okay? The third one, doing the operation twice results in subtracting 6 from your number. So if you're subtracting 6, you need to do in 2 steps, subtract 3, and then subtract 3, right?
Okay.
So just like before, the adding subtracting ones are not too bad.
Right.
For the fourth one, doing this operation twice results in multiplying your number by 4. So if you want to multiply your number by 4, what do you have to do twice?
Multiply by 2.
Right. Okay, so we would multiply by 2 and then multiply by 2 again. 2 times 2 is 4, no problem. The next one, doing this operation twice results in multiplying your number by 1.
1/2.
So if you multiply by 1/2 and then multiply by 1/2 again, do you multiply a number by 1?
I don't know. 1/2
Okay.
plus 1/2 is 1.
Say that again.
1/2 plus 1/2 is 1.
Okay, if you're there, you said,
Pick a number and try.
right. So you also said adding, whereas the operation here is multiplication. So 1/2 plus 1/2 is indeed adding 1, but this one's multiplying by 1.
Mm.
Yeah. So whatever your number is, what do you need to do twice to multiply it by 1?
Multiply by 1.
Multiply by 1.
Right.
Yeah.
So you would multiply by 1 first, and then multiply by 1 again. That would not change the number, so your point would not move. So you multiply by 1 twice.
Okay.
Okay. So the first 5 were okay. This is where they start to get interesting. So doing this operation twice results in multiplying your number by 2. We all know how to multiply our number by 2. That's a scale of 2. What do you have to do twice to multiply it by 2? Oh, it's quiet. No one got this? You can't hear anything?
I couldn't hear you just what you just said.
Oh, so I just said...
Sorry, Ed was muted. Multiply
yeah.
by the square root of 2?
Okay, yeah. So if you want to multiply by 2, how do you do that? We all know how to multiply by 2. So say my number was 8. I would take 8 and move it to 16. That would be my final location. But where would I move 8 to first in order to go from there then to 16? So what did I have to do to multiply by 2? What did I have to do twice? Sorry, somebody said it. What did you guys say?
Marcia.
Multiply by square root of 2?
You have to multiply by square root of 2. So again, I know this is where it starts to get a little interesting for you guys who teach K5 or under. They don't have the idea of what a square root of 2 is, but we should have an idea of square root of 2 is. So here you would say, if I started at 8, I would multiply 8 by square root of 2, and then you would just make some kind of calculation on your calculator. And I don't even know what 8 root 2 is off the top of my head. Does anybody know? Anybody have a calculator in front of them?
Go, Sue.
I have a phone.
I do too. That's what I just grabbed my phone too.
You want to say 8 times the square root of 2?
Yeah, what is that number?
Well, it's going to be 1.414 times 8.
Yeah.
I don't know. So 8 and then 32, so 11.2 or something like that.
That was good calculation, 11.3. So you would first move from 8 to 11.3, and then from 11.3 to 16. Okay. So again, this is where it starts to split off from you're working with children, and now you're working with kids who understand root 2. This next one, doing this operation twice results in multiplying your number by 0. What would you have to do twice to multiply by 0?
0.
Times 0.
Times 0. So again, if you, we'll talk about that in a second. So multiplying by 0 and then multiplying by 0 again is the same thing as multiplying by 0. Number 8, doing this operation twice results in multiplying your number by 1/10. So how do you multiply a number by 1/10?
Times 1 over square root of 10 times 1 over
Right.
square root of 10.
Right, so we would have to do, again, very similar to what we did with the number 2. If it's not a perfect square, we have to use a square root. And if you want to think about it, if my number was 10 and I was multiplying by 1/10, it would move it to 1, right?
Mhm.
So I want to go back through each of these and talk about what they mean in terms of the geometries. And then the last one, doing this operation twice results in multiplying your number by -1. So how do you multiply whatever number you started with? Multiply -1 would move it across the 0 to the other side. What would you have to do twice to get it to -1?
Times the square root of -1.
Right, so the idea is just like we did with 2 and 1/10, is we want to use a square root here. But then what is square root of -1? Where is that on the number line?
Beats me. I can't remember.
Right, so anyone, where is square root of -1 on the number line? I mean, if I point it out, right, where is square root of -1 up there?
Would be between 0.
Isn't it?
Wouldn't
Sorry.
it be positive 1?
Okay, sorry, can I just get one person at a time? Sorry.
Oh,
How about, who spoke first? Lokelane. Go ahead.
Yeah, I don't know. I just said would be between 0 and -1, but I'm trying to visualize it. I cannot see what that would look like.
Right, okay. Jessica?
Well, we're talking about square root is going to be positive, so I was saying positive 1, but it seems too easy, so I might not be right.
Because once you take the square.
Right, so the candidate right now definitely has to be the square root of -1, okay?
It's an error.
And you tried on, yeah, so you tried on your calculator and it says error, right? Some kind of error. Marcia, did you have an input on this?
well, that's I, which is an imaginary number, so it doesn't actually exist visually, right?
Okay,
As far as my understanding of it is.
So this is where if you teach K through probably 7 or 8, you may not even know what square root of -1 is, right? So
Dog knows.
He knows. He's telling us that.
he's trying to give the input here. So the idea is, yes, it is square root of -1, but the real problem is, how do you visualize this on the graph? And many of you said, I can't visualize it on my graph. So let's just make an example here. If I'll put 0 here as a reference. If my number is +1, sorry, my headphones are turned up way, so that really got me. All right, I want to move it over to -1. That's how I want to get to it. So multiplying by -1 would move 1 over there, okay? But I have to do it in 2 steps. So basically what I'm doing is, actually I believe it was Sue, you said it in chat, you said, well, it's a reflection. You're just reflecting across. But how do you half reflect across the number line, right? So the idea is if you're taking 1 and you're half reflecting it across, you're making a rotation of 90 degrees, so to speak. Right there. Okay? Now, Sue, you might be thinking to yourself too, well, what about a reflection out of the plane? Suppose you come off the surface, right? That would still be a reflection of 90 degrees. You would still only go halfway, so a rotation of 90 degrees. Okay? So this idea of if you want to do a 2-stage multiplication by -1, it's a 90-degree rotation. Now, the reason you can't visualize this is that this number is not real. That's the problem. So when we say this, it's going to be the square root of -1, like we had the square root of 2. The square root of -1 is typically defined as the number I. And I is an imaginary number. And where do you find the imaginary numbers on the real plane?
Probably coming out.
So that's the issue, is imaginary numbers are not on the real plane. They have to be on their own type of plane, the imaginary plane. So, and again, this is, I mean, if you're teaching younger kids, this is hard for them to understand. I mean, you have to have the idea of square roots a little bit. But you can talk about it just strictly in terms of the geometry. So first off, how can we visualize this? We drop in another axis. So we have 2 different types of axes here. You have the real axis,
Oh, no, yeah.
and you have an imaginary axis. So what we'd like to do is talk about the properties of this number, right? We want to analyze this and see what else we can do with it by just talking about pure geometry. And so the idea here is just like with transformations, the translations, the symmetries, the rotations, multiplying by this number, which we're going to call L actually, right? Because it makes an L shape, so to speak, a 90-degree rotation, is the same thing as it's just a rotation. That's all it is. But it's a rotation in space. Now we're in the 2D plane. So we're no longer in the first dimension. We're in the second dimension. Okay? Do you want to talk to them?
Oh my. Yeah, Chip just had a mind blown. That's for sure just happened.
Sorry, I'm talking to Linda for a second. I'll be right with you guys a second.
Awesome.
I don't remember ever having a math teacher explain that concept to me.
Okay. So what we want to do then is investigate the properties of this. Okay. So what we're going to do is call this 90-degree rotation L. Okay. And what we want to do is take your number that you started with before and produce new numbers in space. Okay. So for example, if you started with L, what would be 2L?
Let me see. Where's that board?
You have the Hangouts app. Yep. So if you started with, say, the number -1, okay, or 1, either one, okay. If L is represented by doing a 90-degree rotation, what would 2L do?
Same rotation but farther away, yeah?
Right. So how much further?
Twice as far.
Hang on just a second. Okay, sorry. Linda's standing right next to me. We're just getting into the chat for her. So if you do 2L, right, L takes you off of the real axis and puts you up here, but then 2L would be another rotation, so it'd actually bring you back down to -1.
Right.
Really?
So 2L is equivalent to doing multiplication by -1.
Yeah.
Okay? So just based on that idea, we want to investigate some other ones. Okay, so I'm gonna post these up in the window for you so you can see them.
Oh, gosh, okay.
Oh yeah, of course.
Oh, man.
That's going to be behind.
So this is gonna be the fun part, right? I mean, the first part, I remember some of you guys even said, "Oh, why are we doing this?" So here we go.
Can I ask a question real quick?
Yes, ma'am. Go for it.
You have to call me ma'am. So is 2L always going to be kind of the reflection then?
So yeah, that's the idea. Is we want to investigate the idea of what L does. So 2L clearly is a reflection across the axis. So it takes 1 to -1, or if your number was -1, it would be 2 rotations. So it would take it back to +1. So it's equivalent to multiplying by -1. In fact, that was what we established right before we called it the number L, really.
Right.
Yeah.
Okay.
Yeah. Okay. So again, there's in that window there's about 7 of these, I think. Well, 1, 2, 3,
8.
there's 8 of them. Yeah. So what we want to do is just try to figure out what these do to your number. Okay. So you want to try and map them in space and then figure out where they take your number and what it is they're actually doing to your number. So
Okay.
if you have questions, I'm here. I'll be here. I'll give you guys, say, 10 minutes. 10? No? Okay. We'll call it 15, 20, whatever you need. Yeah, and then we'll come back together. If you have questions, just let me know.
So, John, I just want to make sure L is like the visualization of I. So
I'm not making that conclusion.
No. I mean, for me, in order to understand what I'm supposed to do with like -4L, it's going into imaginary plane and
Well,
times
just
-4. I
just
just want to make sure I'm visualizing this properly.
let's just talk about it in terms of the geometry. What does L actually do?
Rotates at 90 degrees.
It rotates at 90 degrees. So we don't even have to worry about what it represents, what it means. We just have to know what it does.
Yep, got it.
Okay, thanks.
Mm-hmm.
One, -2L. The -4, you're back to start. Zero L. Zero. One L, so zero L's. Just pop it one. 1 plus L. 1 plus L. Oh, it shows a translation. 1 plus L, translation. And then -3 plus 3L. And then 3 going that way. So you're coming back out of the page?
Sue, I'm not sure what you're saying. Are you asking a question or are you telling me? And I put you on mute, so you have to unmute first.
Good. I'm trying to visualize this. And when I'm doing the translations, if I'm at a point 1, and then you tell me to translate -3 as the first command.
Okay.
Now I'm at -2
That's right.
at 3L. Or is it -2 still in L?
So if you started from 1,
Mm-hmm.
and then you added -3 to it, you're at -2 on the real. And then you've got to rotate three 90-degree rotations.
I get that part. But
Okay.
I'm at -2 when I slide it. Am I still
Sorry, your audio just cut.
at -2 3L with just the translation?
Okay, your audio cut out right in the middle of all that, so I didn't catch half of that.
That's what happens every time you're talking to me. It cuts out like.
It does.
Oh
It
yeah,
does.
every like 5 seconds. But what I'm trying to say is that initial translation when you're going to -2 and you're in the 1L. And so I'm seeing a translation that's taking you to a different plane, but it doesn't. You're saying no, it doesn't. You're laughing at me. Laugh at me.
No, I'm not laughing at you. Literally, the exact same time that you were trying to describe what you were trying to describe before, the audio cut out exactly at that moment again.
Oh, you're kidding me. Okay.
No, it's the exact same moment.
We're going to try it again.
Yeah, one more time.
If I'm at +1L and I translate.
Okay, so start. You're +1L, and then translate it
to 3L. Never mind.
You're not going to believe this, but it did the exact same thing again.
Okay. This is the last time. If it doesn't come up, it's okay. I'll look it up or something. I'll Google it.
Okay.
It's the translation. When I translate into a negative number,
right.
Am I still in L? Or do I, because I'm in a negative number, move in?
So just so we're clear, L is not a location. L is an operation here. So L is an operation of 90-degree rotation. Okay, that's what we established by doing that. When you do 2 of these, it gets you to -1. So if you're at, okay, so if you're at 1, then you do -3, you would be back here at -2. And then you're doing a rotation of 90 degrees. So that would bring you down here if you're doing 1 rotation. If you're doing 2 L's, that would be another rotation. 3 L's would be a third rotation. 4 L's would be another rotation. So just depending on how many L's it's asking you to do, that's just telling you how many rotations that you have to do.
Okay.
Yeah. And then Jessica, so I'm starting at 5. Then I go to the left 3, which places me at 2, yes, and then 3 positive L rotations. That's right. That's exactly right. And again, since we know that we're now going to be at least in the second dimension, right, because some of these rotations are going to take us off of the main axis, then we have to describe our location in space using now 2 coordinates, right? So what you can do is describe these locations using XY pairs. You're forced to use XY pairs because we're no longer just on 1 axis. Okay, question. Is a positive rotation counterclockwise or clockwise? Good question. So we didn't talk about this before, but if you think about it, we said that when you do this operation twice, it takes you from 1 to -1. So that could be 1 rotation of 90 degrees and then another rotation 90 degrees counterclockwise. Or you could go clockwise and clockwise again. So which one do you want it to be? Positive rotation or negative rotation? Or whatever, counterclockwise or clockwise? Which do you prefer? So as mathematicians, we're forced to assume that it has to be one versus the other. We can't have it as both. Okay? So if you want to define it to be counterclockwise, let's define it to be counterclockwise. If you want to define it to be clockwise, define it to be clockwise. Which do you prefer, counter or clock? Exactly. You have to pick one and stay consistent. Right. You can't just sit here and say, oh, we can let it be one at one time and one at another. Mathematicians don't work like that. We have to define it and we have to stick with it. So if you've been going counter, stay counter. If you've been going clock, go clock. I think most of us have decided to be consistent that we've chose to be counterclockwise. So let's just be more specific that a counterclockwise rotation of 90 degrees is L. Okay. We'll talk about what that means in a little bit in terms of the properties. I think we've got the idea that this is the idea of the imaginary number. All right. So we'll talk about what that means in terms of the imaginary numbers a little bit. Multiply by negative root. Yeah, so if we're just talking about moving across from the real axis to the real axis, it's just a reflection. So anytime you're doing 2L or 4L, basically even multiples of L, all you're doing is a reflection. And again, this is a property that we're going to discover, right, by doing some of these operations.
But then when it goes over there, it is what you said. Because if it ends up over on that side, it ends up over on that side.
Sorry, I was talking to Linda. Okay, so Kelly's ready, Lokalani's ready. Marcia, are you ready? And Sue, are you ready? Okay, got a yes from Marcia. Okay. So what we want to do is investigate what these things do to our numbers. All right, so just looking at the first one, we had, what was it, negative 4L? So what was it that negative 4L did to your number?
Put it right back to the original number.
Yep.
Yeah, so again, this is for you guys, because you're all doing this. So if you did negative 4L, one person says, did it bring you back to your original number? Another person? Seems like at least two people said that, yes, it did bring you back to your original number.
Yeah, for Kelly and I, it brought us back to the same.
Okay, so negative 4L is equivalent to doing, how would you describe that geometrically?
360.
360.
A 360-degree rotation. And again, this was an interesting question that actually came up in the chat, which was, when we define L, are we doing it 90-degree rotation clockwise or counterclockwise? And when you look at the visual of this, you know, when we were doing the factor of -1 graph earlier, I erased it, but if you were trying to go across the axis, if you were at 1 and you wanted to go to -1, you could either go this way and then this way, or this way and this way. So there's two ways to define what you're doing. You could either do a positive 90-degree rotation, which is what we would call counterclockwise, or you could go clockwise 90-degree rotation. So did everyone, I assume everyone did counterclockwise, is that correct? Did anybody not do counterclockwise? Silence. I assume everyone does counterclockwise rotation here for L.
Yes.
Right. Okay. But we could have defined it to be the other way, just so we're clear. Okay. So yes, -4L is indeed a 360-degree rotation. It takes us back to our original point. Okay. The next one is 0L. What does 0L do to our digits? What does 0L do?
I didn't move.
Yeah.
Yeah,
We stayed where we were.
Yeah, so if you're doing 0L, that means you're doing no rotations, which means that you're not moving your coordinate point at all. Therefore, it should still be in the exact same location. Okay, the next one, 1 plus L.
You're going to translate one position to the right, and then you're going to rotate 90 degrees counterclockwise.
Right, so where does that move? So what was your original coordinate point? What value did you choose originally?
2.
What was it, 2?
I chose 2.
2. So where did 2 move to?
I didn't write that. Is it 2 plus L?
So, yeah,
Oh, right?
somebody even said it. I mean, how do you write that? The problem is that 2 is a single coordinate. You're describing it with a single variable. When you write 1 plus L on top of that, you're then moving it off of the real axis. You're moving it off of the axis, which means you now need a second coordinate to describe its location in space. So when you say 2, you actually mean the coordinate 2, 0.
Yeah.
And then when you say I'm doing 1 plus L to it, right, you're moving it to 3, but then you're doing a rotation. So you're moving it from 2, 0. When you add 1 to it, you're doing 3, 0. But then when you do L to it, you're doing a 90-degree rotation, which changes it from 3, 0 to 0, 3. Right? But again, like I said, I didn't expect all of you to get all of these. It's just an idea about how you go about thinking about each of these. I mean, these are hard. The point being here is that when you apply an even number of L's, it's no problem. 2 L's moves you 180 degrees. So if you started at a real number, you're still at a real number. If you do 4 L's or minus 4 L's, as we did in the second example, you're moving it so it does 2 rotations and then another 2 rotations. So it brings you right back to where you were. But this one's interesting in the fact that you're doing an odd number of rotations. You're now doing 1 L, which means you're only rotating 90 degrees, which means you're no longer on your original axis. If you're no longer on your original axis, you need a second coordinate in space to describe where you are.
Oh, shoot.
Right? So is it clear to everyone that we need a second coordinate in space now?
Yep.
Okay, and Sue, I'm sorry. I was just describing where 1 plus L was. So if you started at, say your coordinate was 2, and you did 1 plus L to it, if you added 1 to that, it would move it to 3. But then when you apply an L to it, it's going to move this coordinate into a 90-degree rotation right there. So what the problem is that we used 1 coordinate to describe location here, but now for this coordinate we need a second coordinate. We need an x and a y. So the location of this one would be 3, 0. Right? So if you're describing this location as 3, we can no longer say this is just the coordinate 3. We have to call it 0, 3. So the whole idea of working with L is that we're actually working in the second dimension. We are in the XY plane now. Okay. Queen Lokalane. Do you guys have other questions?
Keep going.
Okay, keep going. Cool.
Yeah.
Just use
Okay.
the board.
What's that? Say it again.
Just use the board so I can hear you, because I can't hear you, but I can hear you when I see it on the board.
Okay, no problem. No problem. So now, hold on, I got a lot of noise coming in here. Oh, that's why the other people from the other room are adding us. Okay, so what we want to do next is -3 plus 3L. Okay, so Jessica, I'm going to mute you real quick.
I'm right here.
Okay, I'm just muting you. Get that crown off me. So if we're doing -3 plus 3L, okay, so let me erase my location. Okay, I'm going to start at 1. So starting at 1, if I add 3 plus 3L to this, so 3 plus 3L, if I add 3 first, that will move the coordinate to where?
4.
So that should be 4. Then I want to add in 3 rotations to this. So I need to describe this with 2 coordinates. So that would be 4, 0, excuse me, 4, 0. And then 3 rotations would move it up here, down here. So if this is at 4, 0 originally, what is the location of this coordinate point right here?
0, -4.
That would be 0, -4. Okay? So that's what it would do to the coordinate 1. Right?
Yeah.
Getting more interesting as we go. Let's skip down a little bit and get down to 1/3 plus 2/3 L. So 1/3 plus 2/3 L. So what does 1/3 plus 2/3 L look like? And again, instead of describing what this does to our number, let's just find out where this is in space.
Yeah.
So where is 1/3 plus 2/3 L at? So again, I'll start from my origin. Where do I need to go first? Sorry, anybody can answer this. Stupid. Okay, so I would need to go out 1/3. So we'll go out a distance of 1/3. So I'll call this 1 right here. So I'll go a distance of 1/3. So initially I'm at the coordinate 1/3, 0.
Okay.
And then I need to do 2/3 of a rotation. So if I do 2/3 of a rotation is 90 degrees. What rotation am I doing?
60.
This must be a 60-degree rotation. So that would be somewhere right here with a 60-degree rotation. Now, I know that the radius of this is 1/3, right? The real issue is then finding the coordinate points for this, okay? And that's the hard part. So if I wanted to find this coordinate, I'm going to blow this up so we can see this a little bit better. It would be at 60 degrees.
Yeah.
And this radius would be 1/3. Okay? So the way that we find these coordinates in space is actually with trigonometry. So we can do that using sine and cosine. Okay? But again, I'm not expecting you guys to know about how to go about doing that. If anything, at least you can visually figure out where that is in space. Okay? You're understanding that you're doing some type of rotation and you're going out some radial distance along that. Okay?
Can you please do this problem?
Yeah, which one is it?
The one right there in front of you with the sign.
Hang on. My I'm sorry. Sue, which one did you want to see?
The one on the board.
1/3 plus 2/3 L? I'm not seeing what you guys want me to see. Jessica. Oh, you actually want to see the trigonometry.
Absolutely.
Okay, sure. So 1/3 plus 2/3 L, it has a radius of 1/3. How do I get rid of that floating crown? I would love to know how to do that. It's driving me up the wall. So what we would say is that the location, oh, now we have a new crown. Yeah, turn off Google Effects. I think that should do it. Okay, so the location of this, it would be the location of the x-coordinate would be the radius times cosine of 60. And the reason that is that you just drop in a 90-degree triangle and make out the cosines and sines. And then the other coordinate would be 1/3 times the sine of 60. So 1/3 cosine 60, 1/3 sine of 60 would give you the exact coordinates for this location. Okay.
It's a special right triangle, though, yes?
Yeah, it's one of the special ones. It's a 30, 60, 90.
Yeah.
So once you know it's a 30, 60, 90, you know all the sides as well. For this one, let's see, cosine of 60, if I recall, is a distance of 1/2. And this one should be √3/2. But then that's for a radius of 1. These are for a radius of 1/3, so it should be √3/6 and 1/6, if I recall. Yeah, I can't remember exactly, but again, you should be able to get it using trigonometry.
So that's 2/3. Okay.
Yeah, something like that. Okay, and then looking at the other ones, I mean, I think the most interesting ones were the fractional ones.
1 square root of 3, 2.
Yeah.
Got it. I'm looking at it.
Yep. So another thing that you can do with this, if you want to completely avoid talking about the imaginary numbers, which is really what we're talking about here, is that you can actually do this just by talking about transformations, doing rotations, translations, and symmetries, right? Because that's all we've been doing, really, is just understanding how to do that in space. And that can be a little confusing for students who haven't been exposed to, say, the second dimension necessarily. So the idea is that if you understand how to do this for certain numbers, then you can talk about the properties of this number L. What does L actually do? So when you apply L twice, we know that it does a 90-degree rotation. right? That's exactly what we established before. And then that begged the interesting question was, we defined it to be a 90-degree rotation this way. That's what we defined L to be. And then another L brings you to -1. So L applied twice. Oh wait, sorry, Jessica. 1/3 plus 2/3 L is the answer. 1 1/3, comma 0. No, it's not, because 2/3 L does not take you to the coordinate y coordinate 0. 2/3 L is a 2/3 rotation, so it can't take you all the way up to the axis here. It can only take you 2/3 of the way, so it can't have a y coordinate of 0. So how do we write the answer? Yeah, so Jessica asked, how do we write this answer then? The way that we do that is with trigonometry, okay? But the way that you guys can write the answer, or if you're teaching this to kids, is just have them to draw the graph and show where it is in space. That show that L, 2/3 L, is a 2/3 rotation. Mute. Yeah. Yeah, all they understand at the time is doing visuals. That's all they can do. Yeah. Okay. So the idea here is we can investigate L. I know if I do 2 times 2 L's, or L twice, and again, I don't want to apply 2L, it's doing L 2 times. It's an operation that I get a factor of -1. Or if I prefer and do -L, if you wanted to find L to be that rotation, this would be -L. So if you do -L twice, I also get -1. So then this is how we go about defining the actually imaginary numbers, okay? So I know that you guys have been told before, and maybe some of us have forgot, that I is the square root of -1, but that's actually not true. I is not the square root of -1. We know that I squared equals -1. That's absolutely true, okay? But the catch here is that I squared equals -1 does not imply I equals root -1. In fact, if I want to solve for I here, I'd have to take the square root of both sides. Somebody keeps adding in here. Sorry. So if I take the square root of I squared and the square root of -1, you think the conclusion might be I equals square root of -1. But the square root of I squared, yeah, that's definitely I. Square root of -1 is definitely the square root of -1. But there's one small thing here that we forgot, which is anytime you apply a square root in an equation, you have to use plus or minus. So when we talk about the square root of -1, it could be a positive 90-degree rotation, okay, or what we called counterclockwise. But it could also be a negative 90-degree rotation as well. So how do we decide which one it is? This is why we just let it be I squared equals -1. It's literally just a reflection across the 0. Okay, it takes a number from the positive side to the negative side in 2 steps. Okay, so this L thing that we've called here, right, this 90-degree rotation, is actually the representative I. We've been talking about the imaginary number the whole time. Some of you had the intuition that it was the imaginary number I, but until, I think many people get intimidated by imaginary numbers. They don't like them. They don't understand them, what they're for. In reality, it's actually just a rotation of 90 degrees in the second dimension. That's really all it is. But I think people get mixed up on it, get messed up on it. They don't like it, and there's no reason not to. Do you guys have any questions about this so far? I wonder why what? Lokalani, what do you wonder? Why they get confused about what? They get lost. Well, you must understand L then completely, right? When we were writing this for MaTCH, the question was, what should we call it? And we came up with the letter L because L makes a 90 degrees. It's actually the 90-degree marker turned sideways, right? So we didn't want to just outright call it I because we didn't want you to get hung up on the fact that this is the number I. We just want to talk about it purely in terms of the geometry, in terms of what it actually does geometrically. Many people, visual learners, absolutely understand scaling, translations, symmetries, rotations. But as soon as you start doing calculations with the number I, they get totally lost on this. One of the beauties is that you don't need to understand the properties of I if you understand rotations. So Marcia asked, why is it when we were introduced to I that it's not explained this way about rotation? I think it's just because many teachers don't understand that that's actually what it is. I can tell you that I wasn't exposed to it that way. I was actually exposed to it by just, here's the definition. I is the square root of negative 1, and here's its properties, and then we're going to use it from here on out. But in reality, one of the reasons is that, we just talk about the graph, is that many people don't get that this is the real axis and this is the imaginary axis. I don't think people understand when you say defining the imaginary axis to be a y-axis. I think that confuses students who are just now learning what the real axis times the real axis is. So where can I get more information about this? We can actually make all the materials available today to you, and then you can actually, if you look up I, it's absolutely online. All of this information is online. I think that just many people have avoided looking into it as for a visual. So if you wanted to look up something, you might hang on. You might try looking up visual representations of imaginary numbers or transformations of imaginary numbers. And then Loki Lonnie asked, when would you introduce this concept? I teach second grade, so please don't say second grade. No, you can't introduce it in second grade that early because the students don't even have an idea. Like the way that we introduce this today, I think would be acceptable, but you have to understand addition, subtraction, multiplication already. So third and fourth grade is probably, fourth grade would probably be the earliest. Oh, come on, it's not that bad. Fourth grade would probably be the earliest. But again, if you can get your students into doing rotations and symmetries and things like that, I think kids can understand that. I think kids can understand that at an early age. Again, you don't have to get into talking about numbers. In fact, if I'm not mistaken, that's kind of what Montessori does, is that they actually don't even talk about the numbers. They actually just, they get them to play around with things, to get them thinking about properties, like how would you make this, like how would you make this symmetry, how would you make this symmetrical. Slope almost killed my 8th graders. Oh man. Yeah, I think visually geometry is fun. It can be fun, but I think that I feel like many teachers don't know how to appropriately teach this to get their kids thinking about it. And it does take time. That's the other thing. Let's see. So there was a third part to this activity, but I don't think we're going to get to it. The idea is that now that you understand what's actually happening when you apply L, what we're going to do is have you apply these to a geometrical shape. So what I was going to have you do was draw your favorite geometric shape in space, and then what you were going to do is take the vertices and apply all these transformations to it. But of course, we're probably going to run out of time. Yeah, Marcia, go ahead.
Well, my question was, I mean, I understand the concept and I can introduce it to my students, but in what sort of concept would I do so? Because like right now, my 8th graders just got finished doing slope and, you know, understanding linear versus nonlinear. You know, you're introducing that concept to 8th graders. I think 7th grade they get the concept of proportionality, but they don't add the b. 8th grade we start adding the b, and I get the whole. Sorry, and so I'm just trying to understand at what point, like what lesson, what teach out could I add this to? Because we, you know, is it when we get to scaling? Is it when we get to more of the geometry? Because we don't touch too deeply on that. I think we do some scaling and a little bit of geometry, but not too much.
John, could you translate that, please?
I was muted, sorry. Okay. Um, so when you're already talking about the second dimension, or R2, it's a little late to introduce it using this style of introduction. Okay, so it's when you're talking about the real numbers or the first dimension only, because then you can get them thinking about, okay, what does this do, translation wise? Oh, what does this do scaling wise? And then you're introducing the idea of, okay, it has to be a rotation in order to get over, so 2 rotations, and then that would give them the idea that they can't be on the plane anymore. So yeah, when you're doing the number line, yeah, when you're talking about rational and irrational numbers, so the idea is once they understand that the real numbers are made up of the irrationals and rationals, then you can explore these properties in the same way that we did. I mean, if you want to even jump to the fast part, which would be, okay, do this twice and get to -1. You could ask them that and have them do an exploration with this. I mean, even this, the way that we introduced it today, would be a great exploration into figuring out how you can get to the idea that you would need some number that's not on the real number line to do this. And then later on, you could come back to that once you start solving, say, algebraic equations. So when I introduce imaginary numbers is when we're solving quadratics. And I talk about, specifically, when I'm doing polynomials, let me write this on the board. We're trying to factor polynomials, and we talk about binomials, and I give them the binomial x squared plus 1. And I ask them, what are the factors of this? And my students, after I teach them, they say, oh, it's a binomial, it's a sum, but these aren't cubes, so therefore I can't do that. Hang on. Jessica, go ahead.
Okay, thanks. I didn't want to interrupt.
It's okay.
We have a question. We're kind of having this debate. So when you're talking about I being the imaginary axis, and I teach an 8th grade math class. Kelly and I both teach Algebra 1, so most of them are high school, but I do have 8th grade. Is the I-axis the same as the Y-axis, or are we talking about a whole nother axis? Because if I introduce this I imaginary axis, is it going to totally confuse them? Because I'm just trying to figure out if it's the same thing or different.
Right, and that was my point, is that's why you have to introduce it before you get to the second dimension, or the XY plane. The XY plane is a real axis by a real axis. It's the real numbers cross the real numbers. Okay. This thing that we're introducing today is the imaginary plane. And it's not something you typically see in a K-12 education, right? But it is not the same thing as the XY plane.
Okay.
Yeah.
Because, I mean, do you think that would confuse them? Because I could potentially introduce, I just had my 8th grade class start.
Yep.
So we are still on, like, real numbers, rational versus irrational.
Yeah. I think it could potentially confuse them. But if you're starting from the real number line and getting them first into understanding the numbers, and then once they understand the numbers, you can introduce the idea of the complex numbers. But it's hard because then you have to differentiate that the imaginary plane and the real plane are 2 completely different things.
Yeah.
Yeah. So, yeah, it could be potentially confusing. In fact, I didn't even see the complex plane until I was in Math 300. So, yeah, I mean, but again, it's something that you could introduce, right? It's just hard. The other way that I typically introduce it, like I was saying, is I start from polynomials and I say, okay, how do you factor x squared plus 1? And they say, oh, it's a binomial sum that is not perfect cubes, therefore it's prime. And I say, okay, but what does it mean to be prime? That means it's not factorable over the numbers that you typically know. Later on, when we get to solving equations like this, we learn radicals and we learn how to solve this equation, which is by isolating and then eliminating the radical by doing square root. So you do get square root of -1, and then I asked them, okay, what is square root of -1? Well, it can't be a number we've seen before, otherwise we'd be able to find this anywhere on the number line. And then when I say, okay, it's not on the number line, what kind of number is it? That's when we start exploring the properties of it. So if you wanted to, once you get to that point, you could then start exploring the properties of it as well and finding out all the properties of I by doing multiplication, addition, subtraction, and division, and exponents, and then going from there. I mean, it's a pretty interesting thing, but I mean, if you understand that I is a 90-degree rotation, you can actually tell me what anything is, like square root of I. I asked my students in class what square root of I was, and none of them had a clue what it was. And then I started thinking about it. I was like, wait a minute, what is square root of I? If I squared is -1, square root of I, and we say I is a 90-degree rotation, this would be doing something twice to give me I. So what would you do twice to give me I? If I is a 90-degree rotation, doing something twice to give me I, that's a 45-degree rotation right there. That's what it actually is. So it's hard to understand when you're looking at the powers of I, you're looking at properties of I. But visually, when you say this is just a 45-degree rotation, students get that. But you can't talk about where that is in space because you need trigonometry for that, which makes it even harder. It's a tough concept to introduce. They struggle with the X and Y axis and plotting. Yeah, many students struggle with plotting as it is. So trying to mix up the X, Y, the real plane, R2, with the imaginary plane, they could get really lost very quickly. So you've got to be very careful. You guys have other questions before we go? I think that we have to go over and do the pedagogy talk now. Where on the graph is 3 plus I? Sure. So 3 plus I, yeah. So we would go out. All right, so if you're talking about the imaginary plane, that would be the real axis versus the imaginary axis. So it literally is just an XY pair, the coordinate 3, 1. If you're talking about the value 3 plus I on the real or the imaginary plane. If you're talking about applying the operation 3 plus I, that would be going out 3 and they're rotating 90, which is something different. So it's a matter of finding the point 3 plus I and applying the operations 3 plus I. Okay, so those are two different things, just so we're clear. All right, other questions before we switch over and go do the pedagogical talk? Oh, one thing I should say about this is people have been asking us to do a presentation on the imaginary numbers for a long time, specifically our high school teachers. Is it normal convention to talk about the operation of I? Absolutely. Sue, we always talk about what does I actually do to numbers? How do you multiply by I? How do you add or subtract I? How do you do operations with I? You can talk about it in terms of L, but I think L is just a visual way to think about multiplying by I exactly. That's exactly what it is using L as a visual representation of using operations with I. And that's why we did it this way, because we thought we didn't want to alienate our K5, K6, K8 teachers that don't ever work with I. We wanted to give them an idea by looking at it geometrically. Because geometry, I think people get visually that this is a geometrical thing once you sit and play around with it. But as soon as you start talking about I think people get intimidated by it. So that's why we didn't want to go with that directly. Now, one of the other teachers has been asking us to do a demonstration about I for a long time. And we wanted to do something that made sense. And the reason why people always ask, well, why do we need I in the real world? Why is it that we have these imaginary numbers, but do we ever see them in the real world? The answer is we actually see them a lot in the real world. It's just that students always ask this too, why do we even need I? So first off, I wasn't even truly established. The properties of I weren't even established until the 17th century. So in reality, it's kind of new to the game. To say that we completely understand the number system is only a recent statement, and I wouldn't even say we completely understand the number system. That's why we have topics like algebraic number theory. We're studying numbers continuously because we don't completely understand them. So imaginary numbers are new to the game in the sense that 0 is new to the game. People think that we completely understand the number system. 0 wasn't even codified as an actual number until the 7th century. So we're talking about only in the last 1,300 years has 0 been on the table. And when you think about that, it's only been 300 years that I has been in use regularly, that people have understand what it's used for, its properties. And we actually see I in a lot of places. Now, many teachers are always asking, well, how can I introduce this real-world applications? And the biggest problem about that is that I is not seen in real-world applications until you get to a very high level. And that's one of the catches. But you can introduce it as rotations. And I think a student gets a better idea about how to do that with rotations than they do trying to figure out where it comes up. So one of the fields it comes up is quantum dynamics. So I studied quantum dynamics in college. We saw I all the time. But the real question is why does it come up into quantum dynamics? And one of the answers is that anytime you're studying a wave, so we're talking about sine waves, cosine waves, any type of wave pattern that light itself is a wave, water moves in waves, electricity moves in waves, any kind of thing that moves in waves has a real component and an imaginary component. So it's one of those things that you see it a lot anytime you're studying those things. Hang on just a second. Linda? So that's one of the reasons it's really hard to talk about it in a classroom at at K-12, for example. It's just one of those things that you can't really bring it into the classroom immediately unless you're doing this kind of idea of rotations. Okay. Do you guys have any questions or thoughts? I've been talking a lot.
I'm good.
You're always good. Okay. Well, if you guys don't have any questions or thoughts, I'm more than glad to jump right into the post write at this time. Give you guys some time to write that out. So I'll post that link in the window right now. There you go. So I'll give you guys about 10 minutes to work that out. All right. And then once we get done with that, we'll switch over to the other room and do the pedagogical talk. And I won't be doing that anymore. So I will be available by headset, though, if you need to talk to me.
Thank you, John.
Thank you.
Yeah, thanks. This was a cool one.
Thanks, John.
For a change? This was a cool one for a change? Is that what you're trying to say?
You blew our minds. You're
It was painful. It was painful.
It's a little painful. At the start, it wasn't so bad. In fact, I even overheard somebody on microphone say, "Why are we doing this? This is stupid." It sounded like one of my students. "Why are we doing this? This is stupid." But it actually is not. I'm not going to blame anybody for it. But,
It wasn't us.
yeah. No. That's accusing people too by saying it wasn't us. But even starting out with something very simple, you can still build into something very complex immediately. So, yeah. All right.
Thank you.
Try again. Hi, can you folks hear me? Okay. Okay. Hi. Testing.
Yes,
Can
yes, I
can
hear
you
you.
hear me?
Sorry. Yes.
Oh, okay. Awesome. Thank you. Hello. Hi, this is Sean. Good to see you folks. Okay, we're gonna get started in a minute or two. Just getting set up here. Okay, ready? Oh, no, that's me. So go ahead and start finishing up if you're not done yet.
Can you just tell them?
Okay. If you can go ahead and start finishing up your post-session rates, then we're going to get started in a couple of minutes here. let's get back together, and we thought that today would be a nice time to focus on one of the math practices that we haven't really spent a lot of time on during MaTCH, which is MP2, reason abstractly and quantitatively. And we're hoping that today's mathematical portion, there's some connections that you can see. I knew what we were going to kind of talk about, so I could definitely hear in the discussion and in when Eric was talking about the numbers, that I could see definite connections to this math practice. So what we'd like to start out with is having you take now this practice is really dense. We kind of noticed that when we were taking a look at it. There's a lot of different ideas in it, contained within it. So what we'd like to give you a little bit of time now is to kind of look through this practice, and if possible, go line by line with someone sitting next to you, and kind of have a discussion about what do you think it means. Yeah, what does each sentence mean, with an eye on these questions here. Why is MP2 significant for developing mathematical thinking? And we're thinking about your students, yeah? Why is MP2 significant? Why would we want students to engage in that? And how would you go about doing that? And what questions does this practice raise for you? Okay, so thinking about these questions and also trying to think about, our experience earlier this morning with the mathematics. What are some connections that you can see to some of the ideas in the practice? Okay, so we'll give you about maybe 10 minutes to. I'm going to turn it back to the practice. So if you can, yeah, go ahead and have a discussion with the person next to you about this practice. What does it mean? Why is it significant for our kids to engage in this practice? Make some connections to how you see it to this morning's activity. Okay.
Hi folks, this is Linda. I know some of you don't have someone to talk with, so if you want to talk with me about some of these, I'm open to that.
Okay, John? Yeah. Okay, so any initial thoughts about this math practice right now? Did you see any connections to this morning's activity? Did you feel like you, or maybe you engaged in in any part of this practice during our math task? Yeah. Which part?
Decontextualize a given situation to represent it symbolically and manipulate it.
Can you say a little bit? Okay, so can you say a little bit? It's on. Can you say a little bit more?
So, like, what we basically did was we kind of took something that is something that we all do in algebra 2 naturally, where we just know how to do it. But in this case, we started from ground zero and we said, okay, how do we make sense of the imaginary numbers now? And by us just starting out with a real number line, something that we all understood from grade school, we're all going, okay, so now what would happen if we wanted to solve this problem of multiplying a number by itself to give us -1? Didn't make sense to us at the time until we introduced this rotation. And once we introduced that rotation, we kind of got into this whole, we kind of got into all the arithmetic and all the fun stuff that you normally do in algebra 2, but you just tell kids, hey, this is how you do it. You know?
Yeah. So, yeah. So the imaginary numbers. I don't know about. I mean, in going to school, I played with imaginary numbers as well, but to make sense of what it meant, what is representing an imaginary number as a rotation, and having that meaning attached to it now is part of that idea of decontextualizing these symbols and these numbers that we use in mathematics. So that's a really great example. Even the use of the number line, representing what happens when you add a number, what happens when you multiply a number to the numbers on the number line. Seeing that happen allows the students or the people who are participating to decontextualize those operations or contextualize those operations and see what those really mean on a number line. Okay, so yeah, so some nice connections there. Okay, so what we have to get in a little bit deeper into this practice, we have some readings that we'd like to offer you, and we'll give you some time. We're going to have some time to read through them today, and there are 2, and you can choose whichever one you want to read. Okay, so let me see. The links to the readings are on the agenda, okay, which I'll put up in a minute. But let me show you what they look like. So this is the first. This is the first reading. Okay, and it would begin from the title where it says classroom examples. Okay, and it's a couple of pages. Okay, it's mostly a vignette of a classroom. So this is one of the readings, and here's another one. This one comes from a MTMS articles from a NCTM publication, Mathematics Teaching in the Middle School. This is a nice article, kind of fun. So we're going to give you some time now to take a look at choose one reading. And it would be nice if you chose a reading that maybe a couple of you at your table might choose a similar reading so that you can have someone to talk with, okay, about what you read. And with an eye on, let's see, so in this reading, so, and so what the idea is, we're trying to kind of connect back to, okay, what does this mean for our teaching? Yeah, what does it mean for students? What does it mean for our instruction? So these are some questions that we'd like you to kind of focus on as you read. How are the students in the reading engaging in MP2? What are they saying or doing that show they are engaging in some aspect of the math practice? Okay, and what aspects of the instruction provide students with opportunities to engage in the practice? Okay. Okay. Oh. Wait, where's the agenda? Where is it? Okay. Okay. Sorry if I'm changing the screens too fast, but so go ahead and pull up one of the articles, and we'll give you about 15 minutes to read them through and talk about how are the students engaging in math practice too, and what's involved in the instruction. What do you notice about the instruction? Okay. Just have a discussion about those two questions. Sorry. I put the math practice back up. So what I'd like you folks to do is start talking about how you saw in the reading. How did the students? What were some of the things that the students did that engaged in some aspect of the practice? What about the instruction provided them the opportunity to engage in that aspect of the practice? Okay, and what I'd like you to do is we have slides for you to edit. Okay, so have a conversation with the people at your table, and you can break up however you want if your table is too big a group. But what I'd like you to do is kind of get on a slide and record down some of your observations about what are some of the things that you saw in the article about what students were doing regarding this practice, and what were some of the aspects of the instruction that provided students the opportunity to engage in that practice. Okay, so if you need the link to the presentation, there it is, it's highlighted right there. Okay, so if you can get to that link, and you should be able to start editing a slide with a group at your table. Okay? And then we're going to have a couple of groups share out. What 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 were some of the things that you saw that how were students engaging in the practice? And what about the instruction provided the opportunity for them to engage in the practice? Yeah. Okay, so our time is kind of getting short, so I'm gonna kind of ask you to finish up your last sentence, and let's have a couple of tables share out about what they thought. Anything about this practice? Is there any table that would like to volunteer and share? Some really great questions and some really thoughtful ideas that you folks put on your slides. So would anyone want to volunteer? Any e-tables? Or no? Okay, I'm gonna roll. Okay, so table 5. Where's table 5? Okay, can somebody from table 5?
You gotta roll again and pick somebody. There's 8 of them, exactly.
Oh, dang it. What am I supposed to say? What were you supposed to say? What we talked about. Yeah.
So if you can talk into the microphone, but you're also talking to everybody here.
So I have to talk normally.
Well, you gotta hear.
We can give her the second mic.
Weird.
Didn't we do that last
Can
time?
I just stand and talk without this mic? Can I just stand without and not talk with this?
The mic is for the
Oh, 알았어.
remote folks. Okay, there we go.
Oh.
Talk into
안녕하세요. At both? Both of them? Okay. All right. So most of our members on our table, we read the, what is it called? Every story tells a picture. So most of us read that, and only one person read the other article. So our insights are mostly on the every story tells a picture. Sorry, this is weird holding both of them. But pretty much we shared that representing the story, the students, they have to represent the story abstractly by graphing the storyline, and the graph represents the good fortune as well as the ill fortune of the story, and they had to justify their reasoning of creating their graph. We shared that students are able to be engaged because they're relating to stories that they already know for most of them, like the Three Little Pigs or Cinderella. And then the teacher is intentionally questioning them to help them lead to higher order thinking.
Right. So if you look at MP2, it talks about having meaning. So making sure that that's a central idea for MP2, where mathematically proficient students make sense of quantities and their relationships in problem situations. So having the graphing as a way for students to make sense of the story and represent the story is a way that the students are engaging in the practice. Okay, as well as so it gets to the idea of contextualizing and decontextualizing. Yeah, the symbols and the representations in the story. And I think another table had let's see, a really good question about the graphing. I think it was table 8 that asked the question, if you use the wolf's perspective and versus the perspective of the three little pigs, would the graphs be inverted? Yeah, and that has to do with, what do those graphs really represent and what do they mean? And having kids, kind of investigate that and think about what those graphs mean. It means that they're going to be working through engaging in MP2. Okay, thank you. Let's have one more table. Anybody want to volunteer? No? Okay, I'm going to roll. Oh, table 5 again. Let's try a different table. Okay, table 3. Somebody from table 3?
No. I did the other one.
Here, Christy. What am I talking about? I'll put up your slide and you put up you. Why do I have 2 mics?
One's for here and one's for the recording.
Oh. Where did I say? Okay, so for the first article, the vignette one, in the article they talked about how the kids were explaining their different ways of thinking, and then eventually they related it to creating symbols for, creating symbols, and then kind of using that to kind of like how we were doing, like creating a rule as to how to solve a problem. Yeah. And then in the second story or article, the one with the graphs, we liked how they, were relating like reading with math, because then you should be doing like interdisciplinary things. And some people were already doing that in their classroom, teaching the kids about working hard and doing things now versus waiting to the end and learning everything for your grade, towards the end of the year. Aspects. Yeah, I don't know what else to say.
Yeah.
Yeah. So that's hearing you talk about that, Christy, kind of reminds me, so linking the literature to the mathematics, that provides a context, right, for the investigation of the storyline and the graphs and the relationships between whatever you want to quantify. So that's something nice in that connection between having a literature connection to the graphing and the mathematics. And if you look at this example, the second reading here, it's an elementary example, but it gives a really nice way or illustration of how a teacher guides the discussion, so that, and it's a little bit different because this is a generalized situation. So the teacher is moving them to notice a pattern and trying to decide having them find a generalized equation, or I guess a equation that symbolizes that particular pattern. And it's a really nice illustration of how the teacher, she still keeps it open and student-centered, but she guides the discussion so that the students do come to see the generalized form of the pattern. So this is a really nice example. And also, if you look at the towards the end of this reading on page 24, and I know this is really small, it says practice 2 essentially describes a 3-step process. Decontextualize, and doesn't, not to say that this is like a particular sequence that you have to follow, but it involves these 3 steps: decontextualizing problems by representing a problem context using mathematical symbols, manipulating symbols such as performing calculations or solving an algebraic equation, and then 3, contextualizing the problems by periodically connecting the mathematical symbols to the problem context. So it's kind of like a back and forth movement between, working with these symbols, these abstract symbols, but always connecting it to the meaning behind those symbols. And I think in today's mathematics session 2 earlier this morning, we saw a lot of that. I mean, that connection between the geometry and the numbers that we were trying to make sense of, seeing them modeled as geometric translations and movements. Okay, so that was kind of what we were trying to get at today, to try and pull everything together. Okay, so you might want to think about, as you know, to kind of sum up, what implications does this have for your own teaching? What are some things in your own classroom? How can you provide opportunities for students to make connections between the symbols that they work with, the equations that they work with, and the meaning behind those symbols and manipulations that they carry out? Okay. Any other thoughts or anything? Yes, in. Sorry.
I think you can do it with
Not both, into both
stories, but you can do it with music. But be careful, because if I were to do Romeo and Juliet, they meet, they get married and have sex, and 3 days later they're dead. It does not give you any of the literature enjoyment that you're supposed to get out of it.
I especially like in that story. I especially like in that story article about how they talk about, well, what would be a boring story? What would a graph of a boring story look like? It would be a horizontal line. And what story? Yeah, they said, right, Lord of the Rings is kind of like a story that would have a horizontal graph because it's so boring to them, you know. So, you know, it's kind of neat. Okay, any other? Yes, Chris. Okay, yes.
On the same lines of what
Okay.
you're just talking about. Because I didn't agree with the horizontal line. So we talked about the idea, especially for elementary kids, that if they had to make like happy faces and sad faces, like if it's a short reading, every sentence, how did that sentence make you feel? Happy face, sad face, or did it make you get involved? How involved were you doing the reading? It made you want to involve more. You'd be above the bar. You didn't want to involve you more. Or if it's a older group and they're reading chapters, this chapter drew me in. This chapter did not draw me in. So at the end of the time you get done reading, you can look at your pictograph and decide whether it was a good book or a good reading. You know what I mean?
Yeah. Hey, thank you. Thanks very much for your participation today. So you know what? So there are things on your tables. There are books and pencils and some flyers. We don't want to take that back with us. So can you please? I don't know how you can decide who can have the books, but you. Please take the books, because we toted them here already the last time and we didn't give them out, and I don't want to keep carrying them around. So thank you very much. Have a good Thanksgiving. Did anybody else want to say something? Okay. Happy Thanksgiving and have a good rest of the Saturday.
So we're wrapping up over here on Oahu. If you guys have questions, I can stick around for a little bit, or if you'd rather, you can just email me the questions as well. That would be fine. You should all make sure and do the post right if you haven't done that already. And then I'll be here for a few minutes. I'm not leaving yet. So if you guys do have questions, I'd be glad to answer any of those as well. Okay, so I'll be ready in just a minute. I'm just going to mute it, wait till the crowd clears out, and then we can answer these questions.
John.
Okay, Marsha, I'm ready for whenever you have questions.
Okay, I actually have two questions.
Okay.
The article that we read, that every story has a picture, whatever, we're actually covering that right now for my 8th graders. We're doing analyzing graphs. So, you know, like situation stories. And so I was going to maybe do that as an activity next week with my students. So that was my first question. And I wanted to share it with the other 8th grade teachers at my school, because then maybe they could also do it as a teach out, because we're using the same pacing guide, and I know the other two teachers are a lesson or two behind me, so they'll be probably covering that lesson next week. Like, I just finished analyzing graphs, and they're actually taking the chapter test Monday, but I thought, well, maybe on Tuesday before we start the new chapter, I'll give that to them as an activity, just kind of review that and touch back, since we just did it today. So will the link work if I share it with my other teachers, the one from the Google that you guys shared with us, with the article itself?
Yeah, about it's a PDF article that's online, so it should be available through that link.
I can just link it to them, and they should be able to see it then.
Yeah, let me make sure. I'm going to click on it one more time just to make sure. I'm almost certain these are just shortened Google links.
Okay, that's fine.
Yeah.
That was the first question. And my second question is, I'm taking this as a PD credit thing.
Yes.
I know we're supposed to do, like activities that we learned in the match sessions, and do I have to collect student work? That was my question about the technical piece for the credits. As far as, okay, I'm going to do this activity with my students. What do I need to make sure to keep for the PD credit portion?
Okay. Let me get a hold of Sean then, because she's the person who's in charge of that. She'll know more than I would. I'm just the math presenter. So
Okay,
hang
yeah,
on
no
just a
problem.
second.
Thank
Okay.
you.
So they should know they need to fix it,
Yeah, if it's a shared link, anyone else will do it. Yeah. Okay.
Oh, Linda, your pens.
You don't have to ask, you don't have to be added into the link. You just click the link and you just share it. Anybody who has a link. Okay. So if you want, should I say like, okay, I'm definitely gonna do it and like tell you now, or well, I figured I would need to tell you all the other things. Yeah. Right? I mean, I can't say that. So I'm gonna go through that would be my deadline, I guess. Okay.
Eric, is there a 10-second diet there somewhere?
I saw it a long time ago, or before the discussion.
I found the 8 one. The 8 one was right here.
Maybe Sean has to.
Oh, okay.
Just to fix it.
And like, can you move that one, or can that? Oh, no, I was for this part, I was.
So there was not a great excuse.
Okay, I'll have to get this time. Yeah, great, yeah. Okay. And both emails, in one email, both. Okay.
Okay.
Hi, congratulations.
So,
What was
you're
your?
gonna be down for
Well, I know I'm just gone just a few days before, so if we meet, I'm gone like the 2nd, 3rd, 4th. So, yeah, if we meet before that to plan, and, yeah, the problem is that I fly home like right after, there's no that week, but yeah. Girls. Webster101.cc@gmail.com.
You must feel really, really proud of yourself. Well, yeah, I'm proud. Now you can relax. I like it. Great.
Ladies on the big island. Ladies on the outer island. This should be all mic and everything. You take the headphones. Turn around.
Huh? Oh, this. Sorry. Wait, I have it in my pocket. Yeah. Hi.
Hi, Sean.
Yeah. Hi, Marcia.
I just have a real quick question. I was going to do, you know, the article that we had today. Every story has a
Yeah.
yeah. My eighth graders we just taught them analyzing graphs, so I thought it'd be a good activity to do as an extension. Now I'm doing this match as PD credits, and so I thought, if I recall correctly, that I needed to submit some student work or something. So I was wondering what the parameters were to make sure that I make sure, because usually I grade their work and give it back to them. So since I'm going to need to have something, I wanted to know what exactly I needed to collect to make sure I had it properly so I could submit it later. So it just copies, I mean, what was the, you know, exactly what I need to do to make sure I have what I need, because once the students have it, I know we'll never be able to cover those documents. So
Right. Yeah. Yeah. So as long as you wanna try and make sure you select pieces that highlight whatever math practice you select for that lesson, you're focusing on for that lesson. So if you're gonna, if you're gonna focus on MP2 for this lesson, then you want to find student work that says something about MP2. It doesn't mean that they have to have like mastered it or acquired, you know, that they're really fluent in MP2. But just that says something, that shows something about their thinking, and that you tried to do some things in your teaching that for MP2, and this is what happened with the students.
okay, so I mean the activity itself lends towards MP2, so I think it'll be effective. And I'm not sure if I should give them specific stories or I should allow them some flexibility with that, because I think some of the students that might engage them better if I allow them. Maybe I'll give them a sample of maybe 3 or 4. You can choose from one of these, or if you have a story that actually interests you, maybe that might help engage some of the students. And do you think it should be a single student, or should I do it as maybe pairs? I'm not sure how to do that, because sometimes some of the students are in my class don't engage very well. And I thought, well, if I do it as a pair activity, but then, you know, if they are not interested in the same story, it's kind of makes that difficult. So I'm trying to, you know, figure out how to best implement this as an activity for 8th graders. And, you know, this is my first year teaching officially, so, you know, I'm just trying to make sure that I make it effective.
Yeah, I mean, if it was, I would have them work in pairs. I mean, that might be a nice place, because then they'll have somebody to talk to, you know, as they're working through the task. Yeah, that might be a good place to start. And I mean, it depends on your class, but I think that's probably what I would start with. It'd be hard for them to do it by themselves if this is, you know, something new. I mean, it helps to have someone to talk to, I think, and work with.
Yeah. And then what I was thinking is maybe I'll even make you know, give them graph paper with already the lines on it, so they don't have to start from a blank sheet. So then they, you know, it gives them a little bit to start with, because I know sometimes it's like getting them to do that piece is hard, sadly. But, you know, if I give them that, and then, you know, the instructions on what they need to do with this, you know, the story, situation, scenario, and what I want to see. And then, you know, that way I can, if they're in groups, I mean, in groups of 2, then hopefully, I mean, if they feel like it, I can actually want a second paper. You know, once you guys get the idea, each of you can choose a story if they choose to do that, or you can both, you know, just work on one. Maybe I'll give them that option. That way we can kind of bounce ideas off each other, at least, even if they want to work on a different story.
Yeah, that sounds good. Yeah.
Okay. Yeah, thank you. And then so you just want examples that show the MP2, if that's the mathematical practice. And then do you also want it linked back? Because obviously analyzing graphs is you know, I use the Go Math book, which is the Common Core standard book. So it's linked back to a Common Core standard, and of course that the teach out originally on the lesson itself was linked to, you know, my pacing guide and my learning targets. So did you need to see all of that or just the MP part for the submission?
No, you wanna put in as much as you can. So if you put in all the mathematical, the content part.
Okay. And then
Include it too.
is it helpful to also attach a copy of the section we're doing pacing guide so you can see the learning target, the CCSS, the Common Core standard that's linked to, and that kind of a thing?
Yeah.
Okay.
Yeah, that would.
All right. Thank you very much. I just want to make sure that I collect the right information so that when I submit it, I have what I need. Because, you know, this is like now, and I'm not submitting this to what, April or May, right? So I want to make sure I'm not going to be able to, you know, regenerate that document later. So
yeah.
Okay.
Totally.
That's all I needed to know. Thank you very much for your help.
Okay.
All right.
Bye.
Have a good afternoon. Bye.
Bye. Okay. Good. Yeah. So how do I?
You don't play video games or anything? It's encapsulating, right? We get stuck into it. Oh, they all left? Okay. Does Sue have any questions before she signed off?
I didn't get her. No, she wasn't there. I just
Okay.
and that was like, it's like dead cheap, and I had to like